Welcome to another episode of the Breadboard Apprentice. In today's episode, we are gonna add this 3-state toggle switch to select between the 3 different modes of our clock module. We're also gonna add a halting signal to our clock module so that we can halt the clock. So let's get to building. I have these toggle switches that can switch between 3 different modes. It is on the first pole, and then it is off and both of them are disconnected, and then it is on the other pole. So I think these switches will be much better to use in our case, where we are actually just switching between 3 of them. So one problem with these toggle switches is that they are not really designed to fit into our breadboards in any way. Previously, I've just used these pin header strips and soldered the switches to them. So this is what we're gonna do now as well. The first mini boss of any soldering job is just to figure out how to position everything. These helping hands are super convenient to hold the different things that you want to solder. However, sometimes it's actually more convenient to use a breadboard. For these pin headers, for example, it's much easier to just stick them down in the breadboard and then tin them. And then you can just hold the toggle switch and heat up the middle pins and stick them together. That is a little mini tip from me. Unfortunately, I lost all the footage of me actually trying to figure out how to create a circuit that would work together with our LS162 to make the switching with this toggle switch. But I have made the schematic that I came up with to form this or to make this selection. This is the schematic that I came up with after much tinkering around to figure out. Now, as I explained in the last episode as well, that these toggle switches also do have some bounce to them when you are switching between the different states, which makes it a little bit difficult how to actually incorporate it. I don't really know whether or not these bounces are that harmful in the case of the switch between the 3 modes. We can think of it as when we are switching from the run mode or the 1 megahertz to the trace mode, then of course we don't really understand exactly when we are switching, since the oscillator is so fast it doesn't really matter. Likewise, when we're switching from trace mode to the manual mode, we could see some bounces if we decide to switch once the clock pulse is high. And really, when are we gonna switch from the trace mode to manual mode? Well, when we want to stop and pulse the clock manually. And of course, when we do that, we really should leave some headroom between the pulses so that we can actually step up to the point where we actually are interested in seeing what the compute modules are doing. So the only sort of real issue that I can think of is if we are switching from the trace mode to manual mode, and this bounces happens to be so fast that it starts to generate pulses that all of the circuitry in the computer can't really handle. Now I'm not sure that that is gonna be the case. I haven't extensively tested all of the bounces and seen what frequency the fastest bounces are happening at. However, this series is really about me learning electronics, so I thought it was a really good challenge to actually try to debounce this circuitry as well. And this is the circuitry that I came up with. So it features 3 resistors, the single pole double throw toggle switch, 2 capacitors, and of course the out signal, the debounced signals. So what we see is that the 2 different throws states here, they are both connected to pull-up resistors, resistor 1 and 2. These are in turn also connected to the capacitors, and these will serve as our RC debouncing circuit. Now let's think about what happens when we are throwing this switch, or when we are throwing this toggle switch to one of these poles. Well, then this pole at this point here and this point here where we are actually, I see here, I should really be drawing some connection points to indicate that those are connected here. Anyways, what we see is that if this lead is connected, this is actually connected to ground through resistor 3, which is a pull down resistor in this case. And so once this is connected, this will be pulled to ground or 0. So in that case, switch number 2 or signal 2 will be pulled to 0. So in that case, we will have 1 at signal 1 and 0 at signal 2. Likewise, if we are throwing the switch on the other pole or the other state, then instead resistor 2 would go to ground, and signal 1 is going to go to ground and be 0, and then signal 2 likewise will be high instead. Now, interestingly, of course, when we are in the middle state, when none of these are connected, then both of the outputs will be pulled high by the resistors and none will be connected to ground. And the capacitors here, the job of them is just to smooth out the transitioning between the two. This of course means again that we need to hook up these 2 output signals to our Schmitt trigger inverter, so in that case all of these will be inverted again. So if we have none of them connected, then both these signals will be 1, but after the inverters, then both of them will be 0. So that is the circuit, so let's just put it on the board. I know it is not recommended to work with live power, but it makes it a little bit more responsive, and you don't have to constantly switch before. And of course here my switch here is broken, so if I push it, it will turn off and it will not turn on again. So instead of hooking up the USB cable all of the time, I decided to be a little bit more adventurous and work with the live circuit, and thus I have to also be a little bit more careful. Okay, I think it's a good time to just slow down and check how the circuit is actually gonna work on the breadboard. So remember, this is our circuitry, how we connected the R1, R2 to power. Then they are both connected to the capacitors, the two capacitors, and then the other side of the capacitors are connected to ground through the resistor R3 here. So, and then the toggle switch are gonna be connected to both these points on the resistor and on this side of R3. Now, when connecting this, we have essentially made the whole circuit. And this is clearly a case where the circuit on the breadboard looks nothing like the circuit that we drew here. And of course, I could have redrawn this circuit on paper to more closely resemble what we are actually gonna do here. However, for a visual inspection, this is much clearer to show. But I just wanted to take a few seconds to show how it actually would look on the breadboard as well, since it always kind of confuses me how to put it down on the breadboard, and I have to think a little bit on it to make it work. And yeah, this is just one of these cases. One of the many skills I hope I will learn soon is how to properly measure and cut the wires that go on the breadboard. It always seems to be either too long or too short. Of course, too long is not a huge problem since you can just recut it. The problem starts when you're actually making the bends, and I don't know how many times you can actually bend these wires without the metal inside them being fatigued and breaking. And that probably can introduce some nasty bugs later on, I'm sure. But for now, I will just do my best. So as we can see, the breadboard is already starting to look quite populated with all the different wires going crisscross. So keeping them neat and tidy is quite necessary to also keep it clear in your own mind. So I really hope that my wiring will improve a lot as we continue this project. And with that done, we now have control as we want. So now we are in manual mode, and if I turn it to the middle position, we are in trace mode. Then at the other position, we are in run mode. So that's all fine and good. Now let's integrate some LEDs to indicate which state we are in as well. So now I have hooked up to two limiting resistors here. They are both on 680 ohms, but when I try to connect my LED here, let's see if I can just manage to get it. Yes, So I can see it shines very dimly. I don't know if the camera actually picks it up because it's some light here. And I realized my mistake. We cannot power it through this direction, not even by removing the limiting resistor, because the pull-up resistor here is 100,000 ohms, which means that the current flowing through the LED will be very tiny. So we need to think of another way, and perhaps the simplest way would be just to pull the signals from the LS or the HTC 14 or 7414, the inverter, the Schmitt-Trigger inverter here, which is the signal that we are also feeding into the selector sheet. So let's try that instead. So now we have the LEDs for the run mode and we have it for the manual mode. However, now how should we actually go about creating our LED signal for our LED? And I'm thinking we have not removed our NAND gate here. We are not currently using it for anything since before we used it to debounce the other two toggle switches that we used before. Now, however, we could actually use it to create a signal to drive the trace mode LED for when we are in trace mode. So let me actually hook that up. The video is already getting quite long, so I will skip over some of the troubleshooting that I did. But if you're interested, I could actually upload a longer cut version of this troubleshooting part, because it does have some interesting sections. The main troubles that I had was with the values for the RC circuit in the debouncing of the toggle switch. The pull-up resistors were at 100,000 ohms and the pull-down resistor was at 10,000 ohms. Those values only came to be for the debouncing to be, or the time constant, based on the ceramic capacitors of 100 nanofarads that I choose. Switching to the electrolytic capacitors of 1 microfarad instead allowed me to use the 1000 ohm for the pull down and the 10,000 ohm for the pull ups, which actually made it work. The reason is that the LS series or the TTL logic actually needs the low signals to be properly pulled down, and when the pull down resistor was at 10 kilo ohms, it didn't have enough capacity to pull down those inputs, which made it not work. At least that is my understanding of my problems. If you have any other explanation of what could have gone wrong in this scenario, please let me know. But for now, let's keep going. Secondly, I was a bit confused how to connect the trace LED. Originally, I thought I could just use the same signal going to the selector IC and just use a NAND gate to drive the LED like this. However, that is of course not how a NAND gate would work, because when the trace mode is active, that means that both the signals will go low. Instead, what I did was I connected the pull-up resistors for the toggle switch to a AND gate that I created from two NAND gates on the 7400 chip, like this. And that turned out to work much better, of course. It is always good to think ahead a little bit of what you should do so that you're not ending up in these logical troubles. Finally, we want to add a way to halt the clock circuit. And we can do that simply by just adding an AND gate and ANDing our clock output with a halting signal. Luckily, we still have two NAND gates from our 7400, and we already saw how to make an AND gate out of those. We also want to have some indication whether or not we are in the halted mode, so we will add an LED as well. And to make this process a little bit easier, let's invert the halting signal going to the AND gate. And luckily, again, we have one final inverter left on our 7414 here. Okay, so now I think we are finally finished with all that I really wanted to achieve with the clock module at this stage. So all that is left to do is now to finally start transferring all of this to a schematic. But that is gonna be for the next episode. Let's just make a final check of all the functionality. So let's start by using manual mode. We can step, no bounces. We go to trace mode, it traces. Let me get a screwdriver and we can check or change the potentiometer. Now we see it goes faster. And of course we also can go to run mode. Then finally we can also halt. That is unfortunately all that we have time for today, but we managed to actually add our toggle switch that we wanted, and we also managed to add a halting signal. Next episode we are gonna continue by transferring all of the circuitry that we built on the breadboard to a KiCad schematic and route it so that we can send it out to one of the PCB manufacturer. I also wanted to make another episode, not on the 8-bit computer build particularly, but a sort of roadmap to all that I've been learning. I first thought to add it as a Notion roadmap, but I quickly got overwhelmed by using Notion, so I will do it slightly differently in a method that I know how to and I have some experience in. So stay tuned for that as well. Bye!